Okay, we'll make a start while others keep coming in. I'm not sure if the clock at the back there is a bit slow, about 5 minutes late by the looks of it. Welcome everyone to the February meeting of the Untitled Astronomical Society, and similar sort of format as in previous months. On this, the front one here, you probably read about and heard on the TV about the latest on Betelgeuse, how the very large telescope at the European Southern Observatory did before and after images early last year and then late last year. And as you can see on the right-hand one, shown on the screen there, how there appears to be some occluding of the stellar disk of the star. Whether or not that's material being thrown out or enshrouded around the star, or whether it's a dark marking on the star, I'm not sure whether they know yet. The lower right-hand one, also from the very large telescope in infrared, shows Betelgeuse as a tiny little dot in the centre, marked there, and Betelgeuse is the sort of out where the radius of Jupiter is in size, to give you an idea of what it is relative to our solar system. And the bright patches show, at those particular wavelengths, show dust around the star, so enshrouding of material is quite possible. Also this week we have the 90th anniversary of the discovery of Pluto by Clyde Tombaugh, and shown there is one of the New Horizons pictures taken of Pluto. And so quite a bit has actually happened. So tonight, do we have any visitors here who've never come along before? Welcome, and our new members officer isn't in the room as yet. She's outside in the kitchen area, I think, Nerida. Feel free to say hello during the tea break, which will be about halfway during the evening. And if you have any questions, ask her, or indeed any of the other members of the society here as well. I'll first of all go through the events that have occurred in the past month since we last met, and it's actually been a fairly quiet month this month, unusually quiet. Then we'll have a talk on gravitational wave astronomy by our visiting speaker from Monash tonight. Then we'll break for a tea break before Sky Murphy will give her take on waves, light and blue is the title. Then Mark Stevens will give Sky for the month. He's nodding curiously at me. And then I'll finish off with the traditional couple of science videos at the end. The first one is one by Professor Max Tegmark. This is now getting on for about 4 or 5 years old, I think, but all about parallel universes and the evidence for that. Then we'll talk about the science of laser hair removal. There's something completely different. So that actually comes from Veritasium, the Veritasium channels by Derek Muller, who's an Australian, but I think he lives in Canada or the US these days. And lastly, we'll show Cody Reeder, and he's chewing on a bit of sodium metal. For those of you who've ever had to deal with sodium metal, it's not something you really want to put anywhere near water. And we'll also look at the reaction of rubidium and caesium in water, which was shown on the TV program Brainiac many years ago. So, what MPAS events have happened? Very, very sparse this slide this month. We had a public night on the 17th of January. Very small attendance, only 41 here. Whereas typically we would fill this room easily, so at least 100. It was 100% cloud, so probably not too surprising. But the numbers of the public nights we've noticed in January and even in February have been down significantly from previous years, so probably due to the impact of the bushfires, and quite aside from the dreadful cloud cover that we've had. 18th of January we had members barbecue and maintenance up here at the Briars. And there was a committee meeting on the 22nd of January where some of the key things talked about was a workshop for other public speakers in the society for speaking to the public and schools, for example, at our public viewing nights here. There was some discussion about the toilets and some feedback we've had from the Briars management about that, and also initial starts to the solstice party as well. And so we're looking for people to put up their hands who might be interested in helping to organise the solstice party this year. On the 7th of February we had our next public night, and again numbers were down a bit. We had 80 there, considering it was only about 5% or so cloud in the sky. Normally we would have expected a lot more, particularly at this time of the year. Now, between now and the next meeting, things are hotting up a little bit. We've got the TLD, the Telescope Learning Day, for the public. The first one for the year is here this Saturday. And at the moment I think we've got 115 booked, unless there have been any more in the last couple of hours since I last looked. So it should be quite busy up here. Members are encouraged to come along, particularly if you've got telescope expertise to share with the others. Most of the audience at this event tends to be people that either haven't had a telescope before, have bought it for Christmas, and are just looking for some hints and tips and how to actually point it in the right direction and what to point it at. So it will be a day of talks, sort of workshopy type things, and then outside to look at the night sky through telescopes during the evening. On Monday we've got Sirius College out at Camp Manning in Mount Eliza, so certainly a venue we've been to quite a few times before, and we're expecting 80 year sixes there. This is the second year they've asked us to do it at that venue. Committee meeting the following Wednesday here. And on that Friday, 28th of February, we've got the Scouts, Pubs and Guides night here at the Briars, and we've currently got none booked for that at the moment, so it's always possible that that may get cancelled in the last day if we don't get any late bookings come for that, but we've only ever had to cancel that once before. On the 11th of March, we've got Parkdale Secondary, that's actually up at their school in Mordialloc, and this is one where they sort of consider us as being part of their STEM program, and they're expecting about 170 Year 7s there for this year for us for a viewing night with the telescopes. So help from any members with telescopes, particularly if you live up that way, would be appreciated. And the next monthly meeting here will be given by Dr. Robert Darney, meteorologist. He used to be a member here until he moved house up to central Victoria, but he does keep in contact with the Society. And he's actually the co-author of the Cloud Free Night website for astronomical viewing. And coming up, we've also got in April NASA, the National Australian Convention of Amateur Astronomers, which is being held up at the Parkes Radio Telescope. Any amateur or professional astronomer, or indeed members of the public, are sort of invited to go along to that. There is a registration fee. And the details are up on the website if you just search for the name NASA, and it's number 29 of those. It's a biennial conference of amateur astronomers covering all of Australia and New Zealand that's held every 2 years. And then no change on the geological expedition down to Point Leo in May, and the solstice party is down getting on for the solstice in June. So, moving on to tonight's talk. You probably saw him come in a little bit earlier, sitting in the front here, and I'll just read a little bit of a bio that I got from that illustrious source, Google. It says we have Ilya here received his PhD in physics from California Institute of Technology in 2008, specialising in gravitational wave astronomy, indeed the topic he'll be talking about, under the supervision of Kip Thorne. And we very nearly had Kip Thorne a number of years ago come out to visit here during National Science Week, but unfortunately it was cancelled at the last moment. Ilya did his postdoctoral research at Northwestern University and at the Massachusetts Institute of Technology as a National Foundation Astronomy and Astrophysics postdoctoral fellow. He then arrived at the University of Birmingham in the UK as a lecturer in 2001 and was promoted to Professor of Theoretical Astrophysics in 2016. And during this time he established himself as one of the leaders in the emerging field of gravitational wave astrophysics. In 2019 he moved out here to join Monash University over in Clayton, also with the title of Professor in Theoretical Astrophysics. And with that I would ask you to show your welcome, and I'll ask Ilya
see if this works. In the meantime, first of all, thank you very much for inviting me here, and thank you for the very kind introduction, and thanks to all of you for coming. And it's a miracle. It worked. Technology is wonderful. I'm a theorist, so a computer is about as close as I get to an experiment. I do my experiments by writing a bit of code occasionally, and so that's for me sort of an in silico experiment. I have to admit that every single one of you knows more about astronomy in some ways than I do, because you know which end of the telescope to look through. I am really a theoretical physicist by training, although at some point I realized that astronomy is actually a very exciting application of theoretical physics, and so I've spent much of the past decade, or a bit more than a decade now, I guess about close to 20 years now, thinking about how to think about astronomy and astrophysics from the perspective of a theoretical physicist. I also realized at some point that I wasn't actually as good of a theoretical physicist as I thought I would be. So it turns out that there are a lot of people out there who are much better mathematicians than I am. I thought I was decent at it, but apparently, it's all relative and in comparison. So I realized, however, that for a lot of topics in astrophysics, it's actually not so important to be a really good mathematician, because it turns out that even theory is only as relevant as the empirical observations. And in astrophysics, unlike, say, some scattering amplitudes in particle physics, where people can compute things out to the seventh significant figure, and this is how good you want your theory to be, so you can actually test it with observations, in astronomy it's often good enough to be roughly right to within an order of magnitude. And counting powers of 10 actually just requires adding and subtracting, and that I can more or less manage. So it turns out that astrophysics is actually, for somebody like me, a theoretical physicist who is not that great at math, is actually a very good field to work in. So that's what I've been doing for the last, as I said, 10 to 20 years. And one of the topics that it turns out is very exciting these days is, of course, gravitational wave astronomy. And so that's something that I'm going to talk about for the next, how much time do you have? About half an hour, 40 minutes?
As long as you like.
Well, at some point when you start throwing rotten fruits at me, I will stop. If you throw fresh fruits, I'll just eat them. So focus on the rotten ones, please. On the front here, we actually have, I'm not nearly as good at drawing either. I actually have very few skills, as it turns out, but there are some people at Nature who are very good at drawing, and so they made this nice diagram to go with a paper that my colleague Alison Farmer and I had written a couple of years ago. And what this diagram is trying to show, and I'll get back to this in a moment, is how you might be able to form the sources of gravitational wave signals. So essentially my plan for today, and it's not too structured, but it's going to be to start out by telling you what these gravitational wave signals are, how people go about observing them, and then to come back to this diagram and tell you a little bit about how I'm using these gravitational wave observations now to try to understand something about how stars evolve and how stars in binaries, stars in pairs, evolve together. So, okay, we are astronomers, right? So what do? We look up at the sky. We look up at the sky, we see it, of course, in electromagnetic radiation, so whether it's visible light, or maybe if we're lucky enough, we have X-ray vision or infrared vision, not so likely perhaps, but then we'll see the sky in so many more colors and wavelengths. That's very exciting. Okay, that's what people used to do. Now, of course, things are much more sophisticated. You have wonderful telescopes out there, so you can look through them. People like me who don't know which end of the telescope to look through rely on somebody else, or hopefully a computer, pointing the telescope for us, and then there's a wonderful image that comes through the computer, and then I can look through the computer and say, look, isn't this marvelous? Look at this beautiful image over there. The sky is amazing. But this is all done in electromagnetic waves, which is not much of a limitation. After all, most of our information about the world comes from electromagnetic radiation, but Nonetheless, as we'll see in a moment, it is a little bit of a limitation. So to explain why it's a limitation, I have to come back for a moment to physics. I promise I'm not going to show any equations, but if we think about fundamental physics, right, we think about one of the most fundamental forces that people have understood for a long time now is the force of gravity. And you know the standard story of Newton sitting under an apple tree in Cambridge and an apple falling on his head, and him realizing that it's all down to the earth attracting the apple, or maybe really what he should have realized is that one shouldn't sit under apple trees when in the autumn when the apples are falling, but he wasn't a very practical man, I guess. And from this collision of his head with an apple, he derived the law of universal gravitation, namely that there's a force of gravity connecting any objects with mass. This force of gravity is proportional to the two masses and inversely proportional to the square of the distance between them. But there are certain things about this that aren't actually very appealing from the point of view of modern science. One of the things is that there's this magical force that acts at a distance. So, for example, suppose that somehow the sun did something completely crazy which you don't expect. It ceased to exist instantaneously, or it exploded in a supernova, which will never happen with the sun, but just let's pretend that it did. We would not know about this even if we were looking out at the sun, if it was daylight, for a good 8 minutes, because that's how long it takes light from the sun to reach us at the earth. But according to Newton's idea of gravity, we would know about this immediately if we had a very nice accelerometer here, because we would see somehow the gravity of the sun immediately changing if something were to happen to the sun. And that just doesn't seem to make sense from sort of the modern physics perspectives. And indeed, Einstein was bothered by this a great deal, because in 1905 he postulated special relativity, which said that the speed of light in vacuum is the ultimate speed limit of the universe. Nothing should go faster than that. And so how can this information about gravity propagate more quickly than this? There were a few other issues with Newton's theory of gravitation. And so in 1915, 10 years after his special theory of relativity, Einstein postulated the general theory of relativity, which basically consisted of two ideas. Idea number one is that mass and energy, which are the same, different manifestations of essentially the same thing according to Einstein, distort or perturb space. And number two, that objects try to travel on the most straight possible path, of course, but now they're traveling in this curved space-time, which means that they're not really moving in a straight line anymore, they're being curved around. And so a picture you might think of as this kind of funnel, so you can imagine there's a massive object somewhere. It's sort of it's a two-dimensional representation of a 3 plus 1 dimensional space-time, so bear with me for a moment, right? It's not an exact analogy, but if you imagine there's some sort of a stretched rubber sheet over here, and I put a bowling ball in the middle of it, it's going to create a bit of a funnel, and I take a little ping pong ball, and I try to roll it in a straight line. Okay, if there was no bowling ball there, it would really go in a straight line, but if there is this bowling ball there, which is creating this funnel, this curvature in this rubber sheet, then of course this little ping pong ball is going to actually go around. It's going to loop around or orbit around the bowling ball, orbit around this indentation in the sheet. And this is what, according to Einstein, really describes gravitation, that objects are perturbed on their trajectories by the fact that the space-time is curved. And when I say objects, this also refers to light. Even light photons would feel this curvature and would be distorted or lensed by the presence of matter. And this has all kinds of exciting consequences. One of them, which Einstein was actually well aware of when he was formulating his general theory of relativity, is that there was this challenge associated with an anomalous precession of the orbit of Mercury. So the orbit of Mercury is eccentric, and according to classical Newtonian gravity, it should just continue moving, the Mercury should continue moving on an ellipse with the sun at one of the foci. Now, in practice, that's not what happens. This ellipse is being constantly rotated, so with every orbit, the axis of the ellipse shifts by a little bit. It's a very small shift. The shift is really about 1/100th of a degree in a century, so of course it's greatly exaggerated in the diagram, but nonetheless, there's too much of a shift. People actually used to think that maybe this was an indication of another planet being present. People talk about the planet Vulcan, that's maybe even inside the orbit of Mercury, and it's causing this perturbation, but such a planet was never observed, and in fact, as the data became more and more better and better, it became more and more clear that there was something fundamentally fishy here. It turns out that actually there is nothing fishy, and that it's very possible to derive the exact orbit of Mercury, and the general theory of relativity does a wonderful job of predicting that. So there are other, by the way, experimental confirmations that I'm not going to discuss today, but for example, in 1919, Eddington had his famous solar eclipse expedition where he and his colleagues looked for the bending of sunlight bending of starlight from distant stars passing by the sun during the solar eclipse. The eclipse was only needed because otherwise there was so much sunlight that you wouldn't be able to see the stars. The eclipse had nothing to do with the actual light bending. It was just to help you see the light in the stars, but what they could see was that the light in the stars, as they passed by the sun, was getting distorted, was getting bent, and so they were seeing this gravitational lensing that I mentioned earlier. So, and general relativity has all kinds of exciting predictions, but it actually doesn't mean that Newton's gravity is wrong, of course. Newton's gravity is still perfectly fine as long as things are moving slowly, or as long as gravity is relatively weak. And there are only a few places where we actually need it, where we might encounter it in our daily life. One of them was something I encountered on the way over here, because I wanted to make sure I arrived in the right place, which required me to use GPS. And actually it turns out that without accounting for GPS, even though it's a big perturbation, but remember that GPS relies on very precise location of you by knowing essentially the delay times between you and signals from several different GPS satellites, which means you have to very accurately solve for the orbits of those satellites. And solving for the orbits of those satellites without accounting for general relativity would lead to very small perturbations in the orbit, but perturbations big enough that you would no longer know whether you were driving to the Mornington Peninsula or towards Perth after enough time has passed, and that would be problematic. So this is one place which I'm very grateful to Einstein, because without him I wouldn't be here today. There's another thing, of course, which is exciting about gravitational waves, which is that in principle they might allow us to have a different way of observing our universe, which is completely independent of electromagnetic observations. And to show you why this is relevant, let me show you what a black hole looks like.
It's a black hole.
No, my computer hasn't died yet, at least I hope it hasn't. This is what a black hole looks like, right? If we look at an electromagnetic light, okay, by definition, it's a black hole. It's called a black hole because nothing, not even light, can escape from inside the event horizon of a black hole. So if you have a single black hole sitting out there, you can look at it all you want to with your fanciest telescopes, and I'm sorry to say this, but you will never see it. Now, okay, this isn't entirely true. There are actually ways of seeing black holes. They generally rely on other things being there besides the black hole. So, for example, here's one way of, well, sorry, before I say this, let me mention that, okay, I sort of already implied this, but a black hole is essentially, typically starts out as a star that's massive enough that it's able to build up a heavy iron core. This iron core ultimately starts contracting. Nothing can prevent this contraction, so it's a runaway gravitational collapse. And ultimately, it collapses down towards a point, something that physicists call a singularity, something that has a finite mass but an infinitely small volume and therefore an infinitely high density. And this generates in our little picture of a funnel and a straight sheet, you can imagine this generates basically a hole in the straight sheet. So it's a funnel that goes all the way down, and so the sides are so steep that nothing, not even light, can get out. So that's the mathematician's picture of a black hole. The film director's picture of a black hole is something like this. So this is a picture from Interstellar, which is a movie that actually my PhD supervisor was sort of involved with and in fact had the idea for. This shows one of the ways you might be able to see a black hole, which is why I put it up here. So if you imagine there's some gas in the vicinity of the black hole, this gas is going to end up, of course, feeling the gravity of the black hole, and if it has any angular momentum, it's going to start spiraling around the black hole. So it's going to be basically be creating rings around the black hole, kind of like the rings around Saturn, and so you might be able to see those rings because these rings are, of course, moving incredibly quickly. We're talking about movement of material in these rings that's at a significant fraction of the speed of light by the time it's getting close to the horizon of the black hole. And so this stuff is incredibly hot, so it's shining in X-rays quite brightly, and very often you can see these things. You can see them, for example, as X-ray binaries, if you're which are accreting black holes, accreting from their stellar companions. If you're looking at, for example, things in our galaxy, Cygnus X1 is a very famous X-ray binary, the first black hole really convincingly detected in the galaxy. You might also see them in the centers of other galaxies as active galactic nuclei or quasars. So people call them quasi-stellar objects or quasars. So these are all hot rings of material, of gas, descending into black holes. You may also have seen some very famous pictures that came out, I guess, about a year ago now, from something called the Event Horizon Telescope, which were attempts to image exactly these kinds of rings around a black hole. But in this particular case, it's showing an artist's impression, and one of the neat things here is that because the black hole is curving space, normally you would expect you could only see a part of the ring, the part that's towards you, but a black hole is able to curve space in such a way that the light from the opposite side of the ring, away from you, is also able to get out and hit your eyeballs. The black hole doesn't actually block it because the light is curved by the black hole and goes around the black hole, and that's why you're sort of in this funny configuration where you can apparently see all sides of the ring at once. So that's one way you can look for black holes. Indeed, we've seen black holes this way. Another way is something that is shown in this animation here, but this animation is actually based on just essentially time-lapsed observations. So these are observations carried out by Andrea Ghez' group at UCLA using the Keck telescope. And let me see if I can play this again. No, maybe not. Let me try it one more time. Okay, so you can see that these are stars moving in the center of our own galaxy, the Milky Way. So we're talking about 8 kiloparsecs, or about 25,000 light years away from us. And you can tell that, okay, for some of these stars, you're only seeing a fraction of an orbit, but for some stars, like the star SO2 here, you're actually seeing over about a decade or 15 years of observations, a complete orbit. And so all these stars are orbiting something, and you can use the fact that they're orbiting something. You can see the size of the orbit, you can measure the period of the orbit. You can use that as a weighing scale to measure the mass of the object inside. Because things shouldn't just be moving on these curved trajectories if there's nothing there, right? There must be something causing them, some kind of force of gravity, something curving the space-time, whatever, however you want to call it. There's something that's forcing them to move in these elliptical orbits. And if you try to weigh the object inside by looking at the properties of the orbit, you conclude that the thing inside has a mass of about 4 million solar masses, so 4 million times more massive than the sun. Now remember, these stars are each about a few solar masses. They're each about 5 solar masses. So if we can easily see these 5 solar mass stars, surely we ought to be able to see a star that's 4 million solar masses, right? Or a conglomeration of stars. Maybe there's a little cluster of stars there that together weigh 4 million solar masses. We see nothing, right? This little white star that's drawn there, that's just drawn there by hand. There is no visible object there. And there is a radio source there, though, this radio source is called Sagittarius A star. Astronomers have lovely non-descriptive names, but because it's sort of in the direction of the Sagittarius constellation. But it turns out that this is the best evidence we have that in the center of our galaxy there's a black hole with a mass 4 million times that of the Sun. So okay, so we can see black holes. I was a little bit facetious earlier. We can see them by other objects moving around them. We can see them by gas moving around them and falling into them and radiating away some of that energy. But for example, what if you had two black holes that were orbiting around each other or maybe even falling into each other? Would you see that? No chance, right? Because now you have nothing but black holes. If there is no gas in the picture, you remove the gas, there are no other stars, there is no electromagnetic radiation coming from these. So that's a little disappointing because people have conjectured for a while that surely if you see black holes in our galaxy, and we presume other galaxies are similar, so there must be some black holes in the rest of the universe too. If we sometimes see these black holes in binaries, then there must also be sometimes binaries consisting of two black holes, and maybe sometimes those binaries merge. And in fact, Einstein suggested something about that might be a way to detect these sources. And it's actually one of the consequences of general relativity that he figured out very quickly after the writing of the theory of general relativity. Only a year later, he wrote a paper about something called gravitational waves. Turns out he got the paper wrong, but a couple of years later he corrected it, and so depending on how you count, 1916 is the birth of the idea of gravitational waves, and 1918 is the birth of the correct description of gravitational waves. So here's the idea. So we're going to go back to the simple picture of space as a kind of rubber sheet. Imagine instead of just putting a bowling ball in the middle of the rubber sheet and letting it create a funnel in the rubber sheet, I instead drop a bowling ball onto the rubber sheet from some height. Now if that's going to happen, it's going to be a little bit like ripples in a pond when I drop a stone into a pond. There are going to be little waves, little ripples propagating out from the place where I drop the stone or from the place where I drop this bowling ball. And these are going to be produced in this case not by me magically dropping something from a different dimension, but by rapidly moving concentrations of mass or energy. And these propagate out at the speed of light, and what they do is they cause space to be stretched and squeezed. So if you want to impress somebody by how tall and skinny you are, all you have to do is wait for a gravitational wave to come along. Here's the gravitational wave passing through. I get longer and thinner. Now, two things. Make sure you get that person who you're trying to impress to look in the right cycle, because half a cycle later, I look like a pudgy dwarf, because of course now I'm being squeezed this way and stretched this way. Also, make sure the person looking has very good eyesight, because the strongest sources of gravitational waves that we likely will ever experience here on Earth are going to stretch and squeeze me by about 1 part in 10 to the 21st power, so 0.20 zeros and a 1 at the end of it. That's the relative change in my size, so not so easy to detect. But in principle, if you could detect these gravitational waves somehow, then measuring their properties could tell you something about the objects that generated these gravitational waves. So there was an idea that came about in the 1970s and was finally made real in the early 2000s, that you could build a new way of looking at the universe by putting together a gravitational wave detector. And so what you see over there is an observatory called LIGO, which stands for Laser Interferometer Gravitational Wave Observatory, which uses laser light to try to detect these tiny stretches and squeezes of space-time that are caused by gravitational waves passing through the Earth and that are due to massive objects rapidly accelerating, such as mergers of two black holes. So let's say a few words about how this is actually done. So I would really say a few words about this because although I've been a member of the LIGO collaboration for 15 years, they quite rightly didn't let me too close to the actual LIGO detectors. These things are quite expensive. There are a few instruments, and each one costs a couple $100 million. So probably a good idea not to let theorists like me to get too close. I was allowed to look at their data and analyze it, and wrote some of the software for data analysis for LIGO. So that was my contribution. But the way it works is there is a laser that shines a laser beam through a beam splitter, which basically allows light to come out along two perpendicular arms. The arms are quite long; they're about 4 kilometers long, and they're 4 kilometers long, so that you can get that little infinitesimal fractional stretching and squeezing to be something slightly more minuscule. By the time the arms are 4 kilometers long, we're now talking about maybe not 10 to the minus 21st meters, but 10 to the minus 17 meters in terms of the absolute movement of the mirrors. Now you might still say, hold on, 10 to the minus 17 meters is incredibly tiny. The size of a hydrogen atom is about 10 to the minus 10 meters. The size of its nucleus is about 10 to the minus 14 meters. You're asking us to measure the length of 4 kilometer arms to a precision of 1/1000th of the size of an atomic nucleus. That's a joke. Well, most funding agencies also thought it was a joke, so it took them a long time to convince the National Science Foundation in the US to invest money in building these detectors, but they succeeded, and rightly so, as it turns out. And when I say they, I mean people like Kip Thorne, Ray Weiss, and Ron Drever from Caltech and MIT, respectively. Ron sadly passed away before the Nobel Prize was awarded for this work, but Kip and Ray shared in the 2017 Nobel Prize for the discovery of gravitational waves. So I'm letting you know that I'm sort of spoiling the story. I'm letting you know that the search was ultimately successful, but I figured you probably heard about this already, so I'm not giving too much away. And the slide goes out the two arms of the detector. It bounces off of mirrors, which are, in this case, not fixed, but basically are painted onto the surface of big blocks of either quartz or sapphire that are freely swinging as pendulums. And so when the gravitational wave comes along, it's going to move those mirrors relative to each other. It's going to lengthen one arm or shorten the other arm, or vice versa. And that means that when light comes back to the beam splitter, it's slightly out of phase, coming back from the two arms because their relative lengths have changed. And now you have a photodetector that's able to detect these tiny phase shifts in the relative light from the two arms and use this to measure or infer the fact that a gravitational wave passed through the detector. So it's obviously a very challenging observation, but here is what a instrument like instrument in Hanford, Washington State in the US looks like. So all of the stuff I showed you is really located in this center control station, except for the two end mirrors, which are at the ends of these two very long arms. Now, there are all kinds of challenges with trying to do this. Of course, you have this very large collaboration, including a large number of universities, a number of them here in Australia, including Monash, that are members of the LIGO collaboration. There's Monash University right over there. Good from the top right. I should probably actually update the slide. I think a few more institutions have joined since I last looked at the slide. And of course, there are a number of technical challenges associated with the detection. For example, for a long time, the LIGO detectors were really good at detecting earthquakes happening in Tahiti, but not so good at detecting gravitational waves because an earthquake pretty much anywhere on Earth would be enough of a perturbation it would sort of knock the detectors out of lock and make them unusable for a few days. Of course, you have all these sources of noise: seismic noise, short noise, which actually is quantum noise from the fact that you have discrete number of photons, discrete number of photons circulating in the detector arms, various thermal noises having to do with the fact that as your lasers impinge on the surface of the mirrors, they heat up the surface of the mirror, and the surface of the mirror starts vibrating because hot things vibrate, so you have basically Brownian motion in the surface of the mirror, so you distort the mirror surface. So all of these things have been terrible issues. There are also some unexpected issues, like for example, here's a local ranger who's supposed to be patrolling this reservation where the detector is built. I don't know how good of a job they do as a ranger if they cannot see giant concrete tubes that are 4 kilometers in length. But in any case, this ranger clearly did not notice where they were going. So that also was actually it turned out that this did more damage to the ranger's car and probably their pride than it did to the detectors. The detectors actually survived that one fairly unscathed. That was a long story, and detectors kept on being improved over the years. They were first built in 2001. There were multiple observing runs separated by periods of commissioning and engineering to improve the detectors. And in 2015, on the 14th of September, there was a apparent signal in the LIGO detectors. And we were all very excited. We spent something like 6 months trying to analyze it and confirm it and trying to understand whether it was actually real. And in fact, as far as we could tell, it was. So we submitted a paper to physical review letters, and here you see the front page of this paper saying that indeed on this day there were 2 detectors that simultaneously observed the gravitational wave signal. 2 detectors were located in Washington State, so this is a few hundred kilometers from Seattle, and in Louisiana, so this is a few hundred kilometers from New Orleans. So that's about 5,000 kilometers between those 2 sites. The fact that simultaneously, within a few milliseconds, you saw a signal in both, which is the same signal, is a very strong indication it's real, right? It's the meaning that it's really a gravitational wave signal. Of course, there are plenty of noise sources that you can imagine. Maybe there was an airplane flying overhead that made the mirror shake, kind of thing. But remember, that airplane would be only flying over one detector. It's very unlikely you have the exact same airplane flying with the exact same pattern, causing the mirrors to shake in the exact same way over both detectors within a few milliseconds of each other, right? So the fact that you're really seeing this consistent signal in both instruments was a very strong indication it was real, and in fact, we could, by analyzing the data very carefully, show that the probability that it was anything other than a gravitational wave signal was infinitesimally tiny, that we expect that we would have had to wait for many hundreds of thousands of years before a signal this loud happened by accident in both instruments. So this was quite an exciting observation, generated a lot of noise. I should also say that the LIGO collaboration was, while it has this very long author list, as you can see, these are just one of the pages of the multiple page author list on this paper. My name should be somewhere a bit higher up there, but alphabetical order, so it doesn't mean that I was any more important than these people. Just these are the V's. But I had a colleague who was a particle physicist who worked at CERN, and he said, a collaboration isn't real unless you have a participant for every letter in the alphabet. And I checked, and the reason I looked at this was that I noticed that at this time, at least I think maybe it has changed since, there was Wu, and there was Yablon, and there was nobody starting with an X. So I think that means that if any of you are excited about doing gravitational wave astronomy, and you're willing to, either your name starts with an X, or you're willing to change your name so it starts with an X, there may still be room for you in LIGO. So this is what the signal looked like. It doesn't look very exciting. It looks like some kind of a chirp. Actually, the gray date signal is the real data, and here are your 2 detectors. This is the detector in Washington, this is the detector in Louisiana. You can see that things match up. So the gray signal is real data. The blue signal is dark blue is basically what you get by, let's say in particular way, smoothing out this data, because some of these high frequency fluctuations, some of these wiggles are just noise artifacts. And the light blue is what you would theoretically expect the data to look like. if it was a binary black hole merger. And of course, you see that there's a fantastic match there. So this is basically the point of this slide. Now, gravitational waves are, in some ways, the opposite of little children. They should be heard and not seen. And so, and the reason I say this is that it's kind of hard to imagine seeing some stretching and squeezing of space-time, especially if it's 1 part in 10 to the 21st. But gravitational waves, it turns out, their frequencies actually in the audio band. So LIGO is sensitive to frequencies of about 100 hertz. That means that, okay, of course, gravitational, you shouldn't think of them as sound waves. Sound doesn't travel in vacuum. But we can play them as sound waves, and so let's see if we can actually get this to work. If not, I will play a gravitational wave for you. One of the although I'm now no longer a member of the LIGO collaboration, but one of the secret tests they do for you to enter the collaboration is whether you can reproduce with your voice box the sound of a gravitational wave. I'm just kidding, but only just about. So let's do this. So this is a movie that my student made when I was at the University of Birmingham, and what you saw on the bottom left were 2 objects, in this case a 1.4 solar mass object, which may be a neutron star, and a 10 solar mass object, which may be a black hole, orbiting around each other, emitting gravitational waves. As they're getting closer and closer together, what's happening is that they're losing energy. So gravitational waves carry away energy. That means the orbit is losing energy. So when an orbit loses energy, that means the objects come closer together. They collapse towards each other. So the orbit is getting tighter and tighter. That in turn means they're losing energy more and more efficiently, faster and faster. So the signal amplitude is going up. And at the same time, the frequency is going up because, of course, the frequency of gravitational waves just tracks the orbital frequency. So as the orbit is tighter, the frequency is higher. The period of Mercury is shorter than the period of the Earth, which is shorter than the period of Jupiter around the Sun. Vice versa, the frequency is highest for Mercury, lowest for Jupiter. So that's exactly what you're seeing here. And so you have this characteristic chirp where frequency and amplitude are going up. So gravitational wave starts out low and goes loud and high. That's your gravitational wave, that's your chirping signal as your binary spirals in. Now it will be a little bit different depending on the properties. So this was a 1.4 solar mass object spiraling into a 10 solar mass object. Here are a 14 and 50 solar mass objects. So the characteristic chirp is still there, but you can tell that it's evolving at a slightly different rate. It sounds a little bit different, and so that means that we can actually try to figure out from the data what the properties of the objects were that were spiraling in, what their masses were, what their rotation was around their axis, where they came from, especially if we have multiple instruments. We're not as good as telescopes are, normal electromagnetic telescopes, but we can at least at some level figure out where the signals are coming from. And all of this information is embedded in the gravitational wave signal. And so I thought this was actually the sort of best sign that really gravitational waves sort of entered the popular psyche was when the New Yorker makes jokes that rely on you to understand something about gravitational waves. So it says there are 2 birds here, and one of them says to the other, was it you I heard just now, or was it 2 black holes colliding? So the implication is that somehow everybody ought to know that when 2 black holes collide, it gives off a chirp signal, which I thought, I don't know what fraction of the readership of the New Yorker realized the joke, but at least it made me feel like somehow we made it into really the true popular press. And of course, that was just the first detection. Since then, there have been a number of others. So here is sort of a plot that some people call the cosmic graveyard, because we're talking about old dead stars. When we talk about units and black holes. And so some of these objects plotted on here are things we've seen electromagnetically. So in yellow, these are the masses in units of solar mass. And in yellow here, between roughly 1 and 2 solar masses, are neutron stars that we know of mostly from radio observations, such as observations of the Parkes telescope that Peter mentioned earlier, observations of neutron stars in binaries in our own galaxy. In purple over here, we see observations of black holes. They were typically observed in X-ray binaries, so these are black holes with other stars orbiting around them. So the yellow and the purple are things we knew before LIGO went online. And the stuff in blue up there, these are the mergers, so this is why they have this funny shape. They're sort of two black holes merging into one. In the end, you're left with a black hole whose mass is roughly the mass of the two things that come together, except for a little bit, a few percent of mass energy, which is actually lost in gravitational waves. So by now, there have been something like 10 announced detections, and LIGO is sitting on probably half a century more, which are there in the data, but they just haven't publicly announced all of them. They're still processing their data from the latest science run. And interestingly, there was LIGO in 2017 observed a merger of two neutron stars. Now, this was really exciting because when you have neutron stars, you have matter, and when you have matter, you have the opportunity to see an electromagnetic signal associated with the merger as well as the gravitational wave signal. So in this case, you saw both an explosion, actually explosion across all electromagnetic spectra. There were gamma ray observations, there were X-ray observations, there were optical observations, there were radio observations. For a while, people have commented that something like half of all of the professional telescopes in the world were pointed at one particular corner of the sky because LIGO saw this double neutron star merger, and everybody got excited, and everybody pointed all of the biggest telescopes around at it. So I was involved, for example, in Hubble observations of this. There were Chandra observations of this. There were Very Large Telescopes observations of this. This is the telescope from which you saw the Betelgeuse observations and so on. So basically, everybody was staring. This was fairly exciting, and the fact that you really saw the gravitational waves and the electromagnetic observations together meant that it was a great confirmation of Einstein's theory, because now we really knew that this was not a fluke, this was really a merger signal, but also we could learn a lot more by a combination of these different strands of observation, different ways of looking at the source. So, okay, that's fantastic. We've seen all of these things. What can we learn from them? Well, and should we actually expect that we should be seeing these things? So, at first you might say, well, yeah, it's trivial. Of course we should be seeing lots of these things. Because stars actually normally come in binaries. Stars don't like to be alone. The vast majority of stars are in binaries. We here are actually a bit of an outlier with our lonely sun, feeling probably a little bit morbid and unloved. Luke Skywalker on the planet Tatooine would have been perhaps in a more realistic situation of having two stars overhead at once. And of course, if you have pairs of stars, then especially if the stars are massive, it's not so crazy. You might eventually make two neutron stars or two black holes, two very dense remnants that are going to merge. So it might look something like this. So here's my best attempt at telling a story of two stars. So here's a binary couple, Stella and Estelle, let's say, are my two stars. And they're not just regular stars, they're rock stars. The reason I call them rock stars is because, like rock stars, these stars burn bright and die young. So that's what massive stars do. A star like our sun is a pretty boring star. It basically sits there for 10 billion years and does a whole lot of nothing. It does something. It's fusing some hydrogen to helium and doing it at a very, very pedestrian rate. When I say very pedestrian, what I mean is that a cubic meter of the sun, right? So we're talking about more than a ton of solar material sitting there in the center of the sun, produces less light than that light bulb per unit time, right? It's if you have if you're used to sort of the old light bulbs, right? Typical 60 watt light bulbs, right? So that means that they're using up 60 joules of energy per second, right? That's what 60 watts means. For the sun, the amount of energy produced by the sun, by 1 cubic meter of the sun per second is about a factor of 500 less than that. Now, the sun compensates by being very, very large. The sun is about 100 times larger in radius than the Earth, which means about 1 million times bigger in volume. So fair enough. It's enough to keep us nice and warm and cozy. But as far as stars go, that's actually quite pedestrian, because there are some massive stars out there that burn through all of their fuel in just a few million years rather than 10 billion years. And they have a lot more fuel too. We're talking about stars that start out being several tens of times the mass of the sun, maybe 50 to 100 times the mass of the sun. And these things only live for 2 to 3 million years, and their luminosity can readily be 100,000 times or 1,000,000 times the luminosity of the sun. Betelgeuse is actually a pretty good example of something that's much more massive and much brighter and much more exciting than the sun. So here are two stars, and they're rock stars, so they're going to be burning bright, dying young. They're also losing a lot of mass and wind. So when you hear about sort of solar winds, again, that's nothing. Solar wind is completely negligible in comparison. These things, in 1,000 years, might lose a whole solar mass worth of material just in winds blowing off their surface. That's my little potpourri over here. But there's one thing that happens to these stars, which is, unfortunately, is not that different from what happens to us sometimes. As these stars age, their waistline starts to bulge a little bit. Stars, basically you can think of a star, this is my theory of a star. A star is a big ball, and in the center of this ball is the interesting part where you have nuclear fusion going on. So it's basically a constantly ongoing hydrogen bomb, fusing hydrogen into helium and producing energy, and this energy is keeping the star from collapsing because this energy is heat converted into pressure, and this pressure is balancing gravity. So gravity is trying to pull in on the star and get it to contract, and pressure balances it and keeps it in equilibrium. At some point, you use up all of the hydrogen in the center, so you fuse all of the hydrogen with helium. The center now is just a ball of helium which starts to contract because there's no more pressure, there's no input of energy, no pressure to keep it from contracting. Now, in the meantime, there is something called the mirror principle, which basically says, look, I'm releasing all this gravitational energy when I'm contracting this inner ball of helium, so my outside of the star is actually going to expand in response to this, and this is how you end up with giant stars like Betelgeuse. So giants, which can get to be 100 times larger than the initial size of the star, they have these big puffy envelopes of hydrogen that expand outward as the helium core is contracting. And so this is what's happening here. And of course, as the star is expanding, that means that even though it used to be at some distance from its companion, there can be some transfer of mass onto the companion, because eventually the tidal pull of the companion starts ripping material off of the star. And so that's what you see in pictures like this. This is partly an observation and partly an artist's impression, which somehow is coming out very pixelated here, so I have to fix this, but it should actually be a better image than this. But basically, the idea here is that you're actually seeing two stars, and we have seen plenty of such objects where there's mass being transferred from one star onto another. Right? So here is this more expanded star, which is usually the initially more massive star, the primary because it begins to expand first, and it's transferring mass onto the secondary. And there can be all kinds of complications with this mass transfer. There's, for example, something called the common envelope phase, where the two stars really are, their naked cores are surrounded by a common envelope of stellar material. That's the technical astrophysical term. So just in case I decided to put a common envelope over them to avoid revealing any privacy of the naked cores in again this sort of kid-friendly picture. Something else that might of course happen to a star is that at some point, if this is a really massive star, the star might actually explode. So at some point, the core is all iron, so if the fusion, nuclear fusion continues until you get up to iron. At that point, fusion is no longer able to release energy. It stops being exothermic and becomes endothermic, so there's no more benefit to continuing the fusion further. The iron core begins to contract, and it's a runaway contraction, and depending on the mass, you either form a neutron star, if the initial mass of the star was less than about 20 solar masses, or it collapses all the way into a black hole. if the mass was more than 40 solar masses initially, and perhaps the outer parts of the material are expelled into space. So here you see an image of a planetary nebula, which is really then to do with planets and is all about the explosion of a star during a supernova and the remnants it leaves behind. And you are left with our friend, the black hole at the end. So I realize I've been talking for too long and probably everybody's getting bored, so I'm going to not go into any detail on this slide, which actually is the stuff that I am working on these days, because I left the light of collaboration. I'm focusing now on trying to understand what these mergers of black holes and the gravitational wave observations of those mergers are really telling us about stellar formation, stellar evolution, supernova, and so on. Suffice it to say that we have been, in the last few years, getting a much better idea of how to pull out this information. And the way that I think about this is that we are kind of stellar paleontologists, right? So if you think about a paleontologist looks at what's left behind. Here's a dinosaur. All the paleontologist finds is a skull or some remnant of the dinosaur, and she, using her knowledge, tries to figure out in reverse how to revert this picture. So how to go from, of course, never having seen a living, walking, breathing dinosaur, how to go from seeing just a skull to figuring out what the dinosaur must have looked like, what it ate, how it hunted if it was a carnivore, and so on. So we are trying to do something similar. We have this program called COMPAS, so Complex Object Mergers, Population, Astrophysics, and Statistics. It's a terrible acronym. I just wanted something that would have a nice COMPAS emblem, and I do know how to spell COMPAS. I intentionally dropped the last S so that if you do a Google search, you're not going to be just sent to your favorite outdoor goods store. And here are a bunch of my collaborators, students and postdocs, who've been working on this code over the last several years, trying to do this kind of modeling of stellar evolution, and then trying to do the inverse science. And the kinds of things we can come out with are, for example, better understandings of pathways that lead to stellar evolution. So I was asked, I was told recently that sometimes speakers show things that are still in preparation that haven't quite been published. So I figured I should follow on this example. So okay, this paper, the preprint of it is actually available, but it's not yet published. So this is quite hot off the press. So this is a paper led by my former student, Alejandro Viña-Gomez, who is now a postdoc in Copenhagen in Denmark, pardon me, and it sort of shows how we think a binary might actually evolve. So here are two stars, forget about all the abbreviations, but two stars born initially, then there's some mass transfer from one to the other. Eventually one of the companions, the first one, the more massive one, goes supernova, and perhaps makes a neutron star. There can be a reverse episode of mass transfer, which we think leads to this common envelope phase where there's a envelope of gas that engulfs the entire binary, and it requires a lot of orbital energy to eject that, which means the orbit shrinks by quite a bit, and so you end up with a much closer system. Maybe you have another episode of mass transfer, another supernova, a very special kind of supernova, because at this point you have stripped off the star from most of its, not just hydrogen, but helium, and finally you have a closed double neutron star system. So this might be the way to make two neutron stars that are merging within the age of the universe. And let me just finish by telling you sort of a little personal anecdote. So this is actually my PhD advisor, Kip Thorne, and I couldn't actually find a picture of Kip with his Nobel Prize. So but this is me and Kip's study holding his Nobel Prize. So that's the real thing. Apparently, I actually learned there are two Nobel Prizes that people get. So when you get a Nobel Prize, apparently you're given two different medals. One medal you're supposed to keep in a safe in a Swiss bank because it's really made out of gold and is very expensive. And the other one they give you, which is sort of a facsimile, which looks and feels pretty much like the real thing, but in fact is made out of some alloy and costs a few dollars to make. So Kip showed us the first, of course, the fake, and then he said, come on, this was a few former students who were visiting him shortly after he got the Nobel Prize to congratulate him. He said, guys, you're all my friends, let me show you the real one, just, be careful with it. So, he pulled out the real one. That's actually the in the nice box is the fake one, and the real one was, okay, in his case, wasn't a Swiss bank because Kip was a very careful person. It was sitting just under his desk. He pulled it out, and we handled it, and so on. And then, of course, somebody at some point was also looking at that one, and then at the end of the day, it was like, which one is the real one now? Oh well, this is a good way to deceive the thieves. I don't know which one is the real one. They'll never know. But the reason I brought up Kip is that Kip is very famous in the physics community for making a lot of bets. So here's, for example, an example of his bet with the late Stephen Hawking, where they're actually making a bet about sigma x1, this black hole X-ray binary I mentioned earlier, whether or not this is real. And in this case, Stephen Hawking had to concede, so there's his fingerprint admitting that it is real. He was making it just an insurance bet. And so Kip has these bets with all sorts of famous physicists, many of which he had won. And of course, being his student, I had always wanted to also have a bet with Kip, to join in the illustrious community of people who had made these bets with Kip. So in 2010, an opportunity came up. Because in 2010, there was actually the first possible LIGO detection. This was predating by 6 years, or 5 years, the detection that I mentioned in the talk, which was the real first detection of gravitational waves. Here, we all knew, because we were members of LIGO, that there was a chance that this could be an artificial signal, because we actually agreed ourselves internally. There was a little team within LIGO, out of the roughly 1,000 people in LIGO, there were 2 or 3 people who were allowed to do what was called a blind injection. So what they were going to do was they could choose to do it or not do it at some point in the science run, and they could essentially intentionally shake the mirrors, using, of course, some software tools. Nobody was actually going to go and physically shake the mirrors, that would mimic a gravitational wave signal. And the rest of us was supposed to analyze the data, treat it all as real, and it was supposed to be kind of a two-way test, right? Because they were not going to tell us until the very end whether it was real or not. And we were, okay, if we failed to detect something that they put in, for example, we would know that somehow our pipelines, our search pipelines aren't good enough, we need to improve them. On the other hand, it would also keep us a little bit more honest and careful, and it would mean that, for example, we wouldn't be getting overexcited, getting ahead of ourselves because we knew there was a chance that this might not be a real thing, it might be a blind injection. But there was such a signal apparently in late 2010, and again, all of the collaboration spent several months analyzing it, and in March of 2011, we all met in Pasadena near Caltech as a collaboration, and having analyzed and having actually written a paper about the detection, describing the properties of the signal, doing all of the analysis, convincing the world that this was it, we voted on whether or not we were ready to submit this paper. And we voted that yes, we thought that if this was not a blind injection, we were ready to submit the paper. So we basically said, okay, we're now going to have a 10-minute break, and then we'll open the envelope, which the envelope was something that the blind injection team had put together, and we would see if it was real. Meaning if the envelope was empty, we were going to press on that day the send button to send the paper to a journal and announce to the world that we could detect gravitational waves. Okay, if there was something in the envelope, okay, we would pat ourselves in the back if we detected hopefully the right thing. Now, okay, the one really embarrassing situation would be, and we actually, I have to admit, we didn't quite discuss what would happen then, is if the envelope was not empty, but we didn't detect the thing which was in the envelope, the envelope said that we should have detected something on February 1st, and we instead detected something on March 2nd, okay, then it would be a question of what we should do. But I was pretty sure that this was not a real thing. And so I came to Kip and I said, Kip, this is my chance for a bet. I know you're an optimist. Let's make a bet. So the bet is a bet between Kip Thorne and Ilya Mandel, whereas Kip Thorne, sorry for my terrible handwriting, I only had 10 minutes to write this, so that's my excuse, although I think my handwriting would be much better if I had 2 hours. Whereas Kip Thorne is an internal optimist and believes that there is a realistic chance that the initial LIGO-Virgo instruments could detect a gravitational wave from a complex binary coalescence. Whereas Ilya Mandel trusts a range of predictions for binary merger rates sufficiently to doubt this possibility. So, okay, basically I trusted myself a bit because that's what I had been working on, is how often these things might happen. And moreover, being a Bayesian statistician at heart, relies on Kip's previous betting history to infer that betting against Kip's optimism is infinitely safer than betting against Kip's physics. So basically, Kip had won, by my count, every single true physics bet, but lost every single bet about deadlines and things of that sort by being overly optimistic. They hereby wager at odds of $100 to $1 that GW 100916, so this event that happened supposedly on the 16th of September 2010, will be revealed to be a blind injection. Signed in Arcadia, California, March 14, 2011, here are the signatures, witnessed by the then spokesperson of the LIGO collaboration. And the drum roll, the envelope. I can say that I'm not responsible for the offense against the English language. This was the then director of the LIGO lab, who doesn't know how to spell envelope, not me. And here's the result. With great sadness, I hereby concede Kip as Thorne. So apparently, I A, won $1, but B, I set the record according to Kip. This was the shortest time between the formulation and resolution of any of his dozens of bets. So I'm very proud of myself. You know, it may not have been the most exciting bet that Kip has ever made, but at least it's in the record book for on at least one count. So that was it. That was the sort of pre-story. The final story is the gravitational wave detector's works, and we can now listen to the signals carried by ripples in space in the fabric of space-time itself. And of course, signals may or may not be exciting. Some of them may be black hole mergers in Carina. Sometimes it may be that Zorlex and Mighty would like to connect in LinkedIn, or maybe that there's a mortgage offer from the Magellan Galaxy, at least in the view of this particular comic author. But in any case, let me leave you with this animation of what a black hole merger might actually look like. This is a numerical simulation on a supercomputer of what a signal from an inspiraling gravitational wave binary might look like, showing the perturbations of space-time and the outward propagating ripples of gravitational waves. Okay, let me stop here. Thank you very much for your attention.
Any questions?
Yeah. The two arms of the device are evacuated.
That's right.
Right. And secondly, you said Brownian motion. Were you talking about Brownian motion in the mirror?
Yes.
Goodness.
Yes, so the surface of the mirror. So there are two separate issues. One is that the surface of the mirror, okay, anything that's warm, right, is going to fluctuate, right? So the atoms are moving, and that means that apparently the average surface of the mirror, which your light is probing, can shift slightly. The other issue is that as the mirror gets heated by the lasers, it actually deforms a little bit, which means that light can now start, instead, even if the mirror was initially set up in such a nice way that light was just bouncing back and forth between the mirrors, once you deform the surface, light starts spreading out a bit because it bounces in other directions and it can hit the sides of the beam tube, which means that now if it bounces back, it actually took a different path because it didn't go from one mirror to the other. It went out to the side and then back, which looks like it went on a longer path, which means that again you might think, oh, well, hold on, my arms got longer, but actually they didn't. It just light bounced in this funny trajectory.
Do you cool the mirror?
So LIGO doesn't cool the mirrors. There is another detector that has since been built in Japan, which is called Kagra, which is cryogenic. So they actively cool the mirrors. What LIGO does instead is it actually uses an auxiliary laser, which in fact heats the mirror, but heats it in a very particular way. It sort of shines from the side and heats it in a way to ensure that it's deformed into the right shape.
Can I ask, with the gravitational waves, I mean, of the detections that there have been, what sort of range away are we talking about from the Earth? Are they all within our galaxy? Or?
No, actually none of them are within our galaxy, and in fact we don't expect it. I think that, so my estimates, my group's estimates are that maybe there are going to be, of these kinds of binary mergers, or maybe sort of one merger every 100,000 years in our galaxy. So it's going to be very rare. We would have to wait for a long time to see one from our galaxy. So typically they come from distances between roughly a million light years away and a few billion light years away. So they're definitely coming from distant galaxies. In fact, some of them are coming from significant redshifts. So redshifts are the way that astronomers often measure distances, in the sense that because the universe is expanding, for things that are very far away, it's actually a little bit confusing to talk about a distance as such. Instead, it's easier to talk about how rapidly is that part of the universe moving away from you if it's far enough away. And so we're talking about things that are, in some cases, redshifts of point few. So that already means that things are moving away at a non-negligible fraction of the speed of light by the time that so the sources of these events are in very distant galaxies. And so LIGO is actually able to survey a quite significant chunk of the universe, and the hope is that future detectors, maybe next generation detectors, will actually be able to see gravitational waves throughout the universe. And that's something very exciting, because we cannot hope to see electromagnetic radiation, any kind of light, from the very, very early universe, because initially the universe was so hot and so dense, it was completely opaque to radiation. So the earliest stuff we can really see is the cosmic microwave background, and that's emitted from when the universe was already about 100,000 years old. Anything within the first 100,000 years, there's no way to see directly with any kind of light. But gravitational waves, they interact very weakly with everything. Now that makes them very difficult to detect. That's why it took so long to detect them, right? But the benefit is that they can also propagate through this hot, dense soup of the early universe. And so in principle, we could use gravitational waves to look into the first second of the life of the universe. It's just a question of getting detectors that are sensitive enough. Oh, sorry.
Very early on in your talk, you mentioned that gravitational waves are not limited by the speed of light. Is that right?
No, they're still traveling at the speed of light in vacuum. They are traveling at the speed of light in vacuum. That's right.
So is there any actual information in the gravity wave that can be used to determine the distance to the origin?
Not directly, but the amplitude of the gravitational wave is telling you it scales inversely with the distance, and that means if you have other ways of figuring out what the amplitude should be, you can figure out the distance. So it's a little bit like actually what we do with stars. I mean, if you just look at a star, you also cannot in principle figure out what the distance is, because it could be that, okay, if I see a bright point of light, it could be that it's so bright because it's nearby, or it could be that it's a really, really, really bright star, but further away, right? But if I have some other way of figuring out what the intrinsic brightness ought to be, like let's say, for example, I look at the color of the star, and I say, well, all stars of this color have the same intrinsic luminosity, then I can figure out from the luminosity, the apparent luminosity, the flux in my telescope, what the distance ought to be. So I can play the same trick with the gravitational waves. And so actually, it's not perfect, meaning we always have measurement uncertainties, and there are some correlations between different parameters, but generally we can figure out the distance down to a level of about a few percent, maybe a few tenths of percent, depending on the signal to noise ratio of these events. Yeah.
You mentioned about trying to sort out whether the let's talk about the amplitude of the merger. It increases. Wouldn't things like an earthquake or something like that be a deterioration rather than an increase in amplitude?
Yeah, so this is one of the ways that you can try to figure out that this thing is real, right? Is that we know that the real gravitation, there are all kinds of noise sources, always, right? You know, something happens that makes the mirror swing, and maybe it looks a bit like a signal, but there are lots of ways to make the mirror swing, but actually accidentally, but very few of them have this very specific type of signature, this specific chirp that gravitational waves have. So really what we rely on to make confident detections is a combination of two things. One, the fact that they have this very specific morphology, which gravitational waves have and other things generally don't have, noise sources. And the second is that we have some additional confirmation from either detecting a very similar signal in multiple detectors, or maybe seeing an electromagnetic source that's coincident with the gravitational wave observation. So for example, if you see a gamma ray burst or a neutrino event, and simultaneously you see gravitational waves, then even if you see gravitational waves in one detector, but if you see them simultaneously coming from the same part of the sky, you'll be relatively convinced that it's unlikely to happen by accident.
So you can exclude the chance of a false positive, say, from a seismic source simply because of the intrinsic characteristic of the signal.
Precisely, and that's basically the game that's played. So, one way you can do this is So, for example, let's say that we're trying to rely on coincidence between two different detectors, right? So this is actually something that LIGO search pipelines do. What they do is they play the following game. They say, okay, let's imagine you write a pipeline, and you say, okay, I have this wonderful black box. I've written this amazing pipeline. It's going to tell me, I feed the LIGO data through it, and it'll tell me when a gravitational wave happened. I say, okay, that's great. Here's my test for you. So you're going to tell me what your threshold is for detection. Now what I'm going to do is I'm going to take LIGO data from one detector from today and another detector from yesterday. And I will line them up without telling you, so I just fast forward one data set by a day and say, please analyze this data. And you say, oh, well, I saw 17 signals that passed my detection threshold. And I say, your pipeline is clearly detecting all kinds of junk because there is no way there should be simultaneous signals in two detectors if the detectors are actually not even taking data at the same time, if they're separated by a day, because there's no gravitational wave that's going to take a day to travel between the two sites. Gravitational waves take 10 milliseconds to travel between the two sites at most. And so this is one way that we can test things, or you can do it in reverse and say, okay, well, how often, if I slide this data relative to each other, how often do you see things as loud as the event was? And if the answer is once in a century, that means I can say, well, my false alarm rate is at most once per century for this kind of event. Now you might say, well, how do you get a century worth of data? You've only been running LIGO for a few years. Well, we can shift things by a day, shift things by 2 days, shift things by 3 days. We can artificially create a century's worth of data by doing different time shifts.
Do gravitational waves exhibit a similar effect to redshift as light waves?
Absolutely. So gravitational waves will get redshifted, and so that means that gravitational waves from more distant sources will look to be lower in frequency than if we were sitting right next to them because the source is moving away from us. And that means that really, because the frequency is actually the best way we have of figuring out the mass of the sources, what we really measure is not the mass, but a mass times the redshift factor. So that's something we can try to deconvolve if we know the distance and we know the Hubble's law, which tells us how redshift and distance are related. We can figure out what the masses really should have been. But absolutely, gravitational waves basically behave just like light in many ways. They get redshifted, they can get lensed. So in principle, you might imagine, and people have even conjectured this may have happened, although I don't think this is real at this stage, that you see two gravitational wave events separated by a few hours, and you say, a few days, and they look very similar, and they come from roughly the same patch of the sky, and you say, how did that happen? How were there two sources that produce almost identical signals a few days apart in exactly the same patch of the sky? And the answer is, actually it was one source. It's just that the light traveled by some massive galaxy and got bent, and what you saw was first light that went like this hit you first, and then light that went like this hit you a little bit later. And so you see this difference in the arrival times of the gravitation of light or gravitational waves. So this happens, we know this happens with light because we've seen this for distant quasars, for example, that are lensed. But this can, in principle, happen to gravitational waves as well.
Thank you.
As far as the existence of gravity, so to speak, does it actually exist in a Newtonian sense, or is it only the effect of mass and energy on space-time?
That's a very interesting question. In a sense, it's not that Newton was wrong, right? It's not that new physical theories say that the old ones are wrong and useless. It's that we say that they're very useful in certain regimes of applicability, and I'd be perfectly happy if I'm teaching first-year mechanics to still teach my students how to compute the trajectories of cannonballs or tennis balls that Roger Federer is throwing up at the Australian Open using Newtonian gravity. I would never dream of telling them, oh, you should use Einstein's gravity to do that, because this is incredibly mathematically complicated, and you get exactly the same result, because for the trajectory of the tennis ball that Federer is tossing up, there is no difference whatsoever. The difference is in the 500th digit after the decimal point, so who cares, right? It's that in some cases we do know that there's a difference, right? We do know that we cannot explain the correct orbit of Mercury to a very high precision using Newtonian gravity, but we can using general relativity. And of course there will be no gravitational waves in general relativity, and so we have seen them at this point. And there are a few other manifestations like that. And so there are some places where general relativity is clearly the more correct theory of gravity. It doesn't mean it's forever the correct theory of gravity. Could it be that in another 100 years we realize that actually we need another modification? Absolutely, because we already know there's a problem with general relativity. We cannot figure out how to mesh general relativity in quantum mechanics. So there's no grand unified field theory that we know of. There are some attempts at it through string theory and so on, but at the moment we know that somehow there's a breakdown at the interface of the quantum and gravity. And so surely at some point a new theory will come up which will replace both.
And it's precisely because of that apparent mismatch that I wonder if gravity exists at all in the Newtonian sense, and there's got to be something else. As in, is there a graviton which they keep coming up with in Star Trek, for example?
So, to the best of our knowledge, the answer is yes, there is a graviton, but because gravity is such a big force, we cannot, there is no observational manifestation of quantization, because to see the quantization of something, it means you basically must be at a level where you can detect individual objects. So we can, electromagnetism is a sufficiently well understood and well measured force, and sufficiently strong force that you can, with modern instruments, detect individual photons. Actually, you don't need modern instruments. Our eyes are very good at that. Our eyes are able to detect 2 photons, it turns out. 1 isn't quite enough, our eye won't register it, but 2 photons our eye can register, actually. So we know that light is quantized, but with gravity, a single graviton worth of gravity is so infinitesimally tiny that it's absolutely beyond the capability of any modern instrument to detect. So
it could still be there, it's just so small we can't.
Indeed. So we're just not at a level where we can really test these kinds of ideas experimentally.
Very go on.
Perfect.
Can I ask one other thing?
One last question, John.
Is it increasing entropy or decreasing entropy?
Well, the universe, as far as we know, is still generally increasing entropy.
Event.
This particular event, that's actually a very good question, because black holes are these very funny things. That this is actually one of the other bets between Kip Thorne and Stephen Hawking has to do with what happens to information that goes down a black hole.
Happens to my computer.
I'm sorry?
Happens to my computer.
Yes. It can happen in some practical settings, but in particular, maybe that's best to leave for tea, because that's a longer discussion. But the answer is, it's not entirely clear what actually happens to the information that goes down black holes, because quantum mechanics says we should be able to pull it back out again, and in principle, and Hawking radiation says that it's completely thermalized, and so this information is lost, and so the answer is it's tricky, and it's also tricky because in general relativity things aren't very localized, so it's actually an interesting question where the gravitational waves, they aren't really coming from inside the black hole, they're sort of coming from the surroundings of the black hole, from the space-time around the black hole, so there's no specific point that you could sort of point to and say this is where the source is. There's no actually localization of energy in general relativity, so things get quite messy here. So there's no simple answer. At least not that I know.
All right, well, with that, I think we'll stop for tea break. I'd like to thank you very Okay, we'll break for 15 minutes now, and reconvene here at, say, 9:45 by that clock, and to continue on for those who wish to stay.
Hi everybody. With the previous speaker talking about waves, gravitational waves, I'm afraid this talk is going to be at the level 101. But waves are extremely fascinating. The more you look at it, the more it's like opening a can of worms. And I must say that quite a number of words that he said were actually the words that I already prepared for this talk. So you're going to hear a few repeats. Please notice that, is my laser? The sound that you just heard is actually a light curve from a star that has been translated down to sound wave. So it is actually extremely interesting. Next slide, please. And by the way, the title, if you didn't get the joke, it was supposed to sound like, what was it again? Wave, light and blue. It was supposed to sound like red, white and blue, but this case is waves, light and blue. So with wave, we do know quite a lot about that, and we thought, okay, waves, we just change force back and forth, and then that would produce waves. But in fact, when there is just a steady force, like wind over water, you can also generate waves. And in fact, that crest is part of a shock wave. So a sudden force, even once, can create a wave. And many people who've done physics before at some stage will probably remember about a system where you give an input and then some response will be going ring like this. So that's a kind of a wave. Whereas some other system will take forever to come up to a new state. Then some other systems could be designed to be responding a bit faster but without waves. Talking about shock waves, when you have extremely shockingly sudden force, you can create earthquake kind of shock wave. But that's not quite true because it depends on the medium as well. You can have, for example, shock waves from the supersonic jet or a bullet, and that's not sudden, that's just traveling at a steady speed. There are several kinds of waves, shock waves in astronomy. Somebody's reading that for me, please?
I got volunteered for that. In astronomy, there are some examples. Supernova shock waves. The Bayer shock caused by the Earth's magnetic field colliding with the solar wind. Shock waves caused by galaxies colliding with each other. And the meteor entering events. And on a local basis, we had a shock wave last night. And Anna, my dear woman, went out through the front door, let the dog out, and at that moment, a lightning bolt struck the tree across the driveway. And you should have heard the shock wave.
Okay, thank you so much for that. How topical. So remember that the medium is quite important, just like experiment with corn flour. When you mix it as a gooey, syrupy thing, you can stick your finger down and then you can even make waves with that. But if you suddenly land on it, it will become quite like solid. So we'll come back to another kind of shock wave later on, but next please. The previous speaker talked about gravitational waves, and a physicist, a real physicist, told me that gravitational waves are expected, of course. It would be, the whole physics would break down if there's no gravitational waves. So, okay, fine. Just like other kind of forces, there's a force field that is quite fascinating. I'll skip this a little bit and go on to the next one. Because from childhood, and I haven't really grown up, magnets are still amazing and magical. With the magnet, like other forces that's produced, invisible, cannot feel it, but we can watch the effect. And just in case you've forgotten or you've learned in school, you can demonstrate magnetic fields like that, and it goes all around. Okay. And we can make magnetic force, of course, with a piece of wire and steady current. Remember? You wrap that around, flow that, and then you can have magnetic north, the force going that way. And if this electric current is alternating, you can have this magnetic force alternating as well, being a wave, a field. And that's the principle of motors, of generator, etc. And the reverse is true. If within this middle here, you're generating electricity that's going back and forth, you are creating magnets, magnetic field all around it. And what happens? This is the principle of antenna. You're having electric charges going up and down here, alternating. You're creating magnetic force all around this. And we don't have time, but remember how you determine the electric field direction, magnetic field direction here, and that's the direction of propagation. Okay, so antenna. Someone has a question that I planted.
I've been asked to ask, can a radio antenna emit light?
Can a radio antenna emit light? Have you asked yourself a question? Because everything is just electromagnetic waves, remember? Whether it is 50 Hertz, or whether it is radio waves, or whether it is visible light, or gamma rays beyond that, it's just electromagnetic waves. Can an antenna emit light? Questions are more important than answers. You can read up, please, afterwards, because it's very exciting. I can give you a hint that, yes, it can be designed in two ways. Next, please. Now, the best force of all is electricity. I'm a little bit biased. Electricity, force field, as mentioned before, electricity and magnetic forces are very coupled together. Next slide, please. They are so bound up together, we don't know why, but they just happen like that. And we are swimming in it. We are everywhere in it. It doesn't have to be man-made, human-made, or anything. Anything, anywhere in the whole universe is just filled with electromagnetic radiation. Yes. And in fact, it is very amazing that we can detect anything at all because they all mix up together. And just like the sonic boom, it's not so much the shock wave of a jet plane going through. It's the waves that are interfering with each other, and they subtract sometimes and they add sometimes, and that's the boom that you hear. And it's like the meteor event as well that enters the earth. Right, there's a sonic boom happening there. Don't look too puzzled with the difficult questions, not for today. So, electromagnetic radiation everywhere, okay? Next, please. And light, just to emphasize, is nothing special about it. It's just humans. We're just egocentric. We're just human-centric. We just think that light is so special. It's just one little band in the whole long, wide band. But since we've got eyes anyway, might as well feel special about what we see. But with light, remember I mentioned about the light curve? It's the group light, the whole light, a star or whatever, that's the whole lot of the light, and the amplitude would go up sometimes and down sometimes. Like we have the monitor here, the light monitor, and Peter can produce the light curves detected on site, and we can watch what happens. But next, my special interest is the composition within the white light that we see. It's just so amazing how that was detected. And you can read up all about some clever people, like millions and billions of people on Earth. And then when a prism was shown to split light, people were thinking that, oh, there's something to do with the prism, the quality, the characteristic of the glass to split it. And then Newton actually took just the one red strip and then put it through another prism and nothing changed. So he made the conclusion, apparently, that it's nothing to do with the glass or anything, it's something to do with the light. The original light had all sort of colors within it. And even with my interest, I sort of didn't think too much about it, but the light from prism is produced one way, with the violet on the outer side and the red on the inner side, and diffraction grating produces multiple strips of rainbow or star ball, light ball, but the violet's in the middle and the red on the outside. But rainbows, think about that. When you have double rainbow, they're upside down to each other. But what happens if we go back one, please? My favorite. As you see, that is the test image from our site here. Look. Oh, I forgot to say, that's Eta Ka, plus other stars around this. And see the strip of lights, the violets in the middle and the red on the outside. Of course, that's quite overexposed, but you can see all other stars produce. When you look at this, you know that, oh, from this star, because the violet's here and red on the other side. And then there's some more. But anyway, with Eta Ka, apparently, many people here will know about these more than I do, but apparently, when the event happened, it was known that Eta Ka is non-stellar because it's just so weird. It didn't destroy itself. And when it's said that it happened 170 years ago, as you know, Eta Ka is 7,500 years away from us. So in fact, it happened all that time and the light only got to us about 170 years ago. And it has been apparently thought that it didn't destroy itself because that event that actually created all these gas clouds around it, the nebula, the event was probably a shock wave exiting from inside of Eta Ka, and it still leaves itself intact. So there's still a lot of interest. And by the way, Greg, who's not here tonight, wanted me to remind everyone that Eta Ka was named Eta because at that time it was quite faint. But now it's becoming quite bright. So bright that it's actually harder to detect certain properties about that.
No, it looks a bit like a fried egg through the telescope.
Delicious. But, oh, I'll talk about that later. I mean another time about spectroscopy. All sort of stars, as you know, everyone knows that they all look different like that. It's not like, oh, they all look the same, everything boring, but every star has its own characteristics, and when you feed these into the software, of course you get all the intensity at different types, and you get the chemicals, hydrogen lines, etc., emission lines, absorption lines. So it is extremely characteristic, like when I look at your face, I recognize you. So some people, when they look at this, they recognize what star this is. Now that one is actually the most important slide, because a little while ago during a presentation, not by me, by an expert on spectroscopy related area, a question from the audience was, how come we have blue shift, sorry, ahead, forward please, one. how come we have blue shift, red shift when there's nothing in space? There's no medium light when we talk about the ambulance sound, that we imagine that, okay, the sound waves just getting pushed together and you get higher frequency. What happens with the outer space? How come we've got that? So I would like to try to explain this, because I'm hoping that that particular presentation from Monash University actually would be hopefully shown to us sometime, and there'll be a gap when people were struggling to try to explain this. Let me try to explain this to you. Suppose I'm a green star. Now, are there green stars in the sky? And if not many, why not? I won't discuss that. You don't have time. I'm supposed to talk for only 10 minutes. So suppose I'm the green star and I'm 1,000 light years away from you, and I'm emitting all the time this light, the green, the top one, okay? From negative to the peak, to negative again to the peak. And 1,000 years later, you will pick up the same negative, peak, negative, etc. But after I produce a negative, I'm going up to peak, but I'm moving towards you. Why I'm still steadily producing that? By the time you pick it up, the peak will arrive at your spot, not in 1,000 years, but it's in 1,000 minus that time. So relative to what you would expect from the green, now you're detecting something with the peak arriving a little bit earlier. And if that continues to happen, you will keep seeing your margin on blue star, on green star, now appearing blue to you. Right? Okay, so we don't need any medium, any solid, like sound wave in space. That happens. So we get a blue shift and of course red shift. By the way, our eyes or detector that are designed to detect this strip, we just keep seeing that same strip. However, the star shift in anything, you keep seeing that strip. So it's not the starboard strip that you see shifting, but the pattern within it, which should occur at certain points. Now the whole lot get shifted. So when you see the pattern shifted towards blue or towards red, you know that something is moving away or towards you. But more exciting than that, if you keep observing this and then I think you know all this, I'm just getting excited thinking about it. If you see a cycle of coming blue and then red away from you and then blue again, you know that something is circling around like this. Okay, so my favorite topic, next one please, is the most exciting of all to me. A lot of things can be discovered by that. But what was I going to say back before? But it's actually not the most exciting, not the most important thing. The most important thing in astronomy or in everything is actually not one single field, but it is the collaboration of all the fields together. So standing on each other's shoulders. And that's why also, as I said a couple of times, that part of the reason I'm here, not only was it because Peter asked, and I always say yes, is because the society actually really needs more speakers. And this is a perfect platform for people to please come out and produce in whatever field, not only in astronomy. I haven't had a chance to ask Peter before, but Peter told me that we have something in the society, a charter.
Constitution.
Would you like to tell people? They won't believe me that it's not just astronomy, but it's the whole science.
astronautics and general science.
Yeah. So please, in particular, anyone, please tell all your family members, in particular, anyone going through school and university now, they are already trained up to do presentations. They are already doing those. Please ask them to come and do this here. And if not, take a video clip of their presentation and send it to Peter, and then we can have a share of that knowledge and skill. Last, a little bit more important or more interesting than that, is actually about light. We are still on about light. We, a lot of times, I think, repeat what we read or have been taught, or we thought we've been taught about facts in science, and we're not thinking hard about that. There is a question about, can something travel faster than the speed of light?
Yes. Particles have been accelerated to travel faster than the speed of light in a refractive medium, where that speed is slower than the speed of light in vacuum.
Fancy that? Thank you so much. And even if it's not in the refractive medium, you know what that all means, right? Because, you know, in space, there's that fixed speed of light, but in the refractive medium, light travels more slowly. That's why some particles can be accelerated to the speed of light, but that's higher, faster than the speed of light in that medium. But related to what someone around here asked before, I wholeheartedly believe that, you know, as we all know, what we know about science now is just a fraction. We will discover something else, not just the electromagnetic radiation that we are swimming in. Okay, with that, I would like to say, wave you bye.
Mr. Stevens, time for the month.
While he's doing that, I'd like to make a comment of an interesting observation. Because your eyes are more sensitive to brightness than they are to colour, if you see a rainbow at night with the moon as the source of light, it's in shades of grey. I saw one about 10 years ago on the freeway, and it's quite fascinating. This beautiful rainbow in shades of grey.
Yeah. That's so wonderful.
Yeah, it was. It blew my mind at the time.
Take a photograph.
Mr. Chairman, President? Yeah.
Thank you.
Still there, is it?
Sorry?
Behind the bushfire, smoke, dust and rain.
I
Sky
used to
still there.
go to a pub called the Magnet. I used to call it the Magnet. It was really called the Valley.
Righto, I'll try and speak a bit quicker. Sky for the month, February 2020. February, March 2020 highlights. Looking at a full moon on the 9th of the 2nd. Mercury at full elongation. Now, what you'll notice is I've coloured some of the terms there, and it's just to try and, particularly for the newer members, most of the old members will know what they're talking about, but in terms of elongation, when Venus and Mercury come around the Sun, or disappear back around the Sun, they travel a distance from the Sun and then back again into their conjunctions. And the best time to view them is when they're at maximum elongation, and elongation is the angle between the Sun and the planet itself. The Moon at perigee on 11th of the 2nd, that's its closest point to Earth. Mercury at inferior conjunction, 26th of the 2nd. That basically means Mercury and Venus have two conjunctions. They don't have an opposition because they're closer. So the inferior conjunction is when the planet is between Earth and the Sun. Apogee, Moon at apogee, it's the furthest point from the Sun. seems to happen fairly quickly, but you just got to realise that a lunar month, on average, is about 28 days. And Venus is perihelion. That basically means Venus is approaching its maximum closest approach to the Sun during its orbit. As for the sky, looking south, you'll notice from last month there's not a lot of change in terms of what's visible. Obviously, you know, the Epicurus, everyone's discussing how to pronounce it. I'm calling it Epicurus. You have the Tarantula Nebula, which is actually in the Large Magellanic Cloud. And for those who like looking at globular clusters, you've got two. You've got Omega Centauri and you've got 47 Tucanae. Looking to the north, you've got the Orion Nebula, obviously in the soil of Orion there. You've got the Ghost of Jupiter. Now, if you compare it to last month, it's moved a little bit. What you'll notice with these, as you look to the north, everything tends to move a little bit to the left, and as you look to the south, everything seems to go around the South Pole. So that's why there won't be a lot of change month to month.
Venus is too bright.
What are the planets up to? Mercury reaches its maximum elongation on the 10th of February. That's the best time to view it, but apparently it's going to be in the twilight, so you're not really going to get to see too much. By twilight, it means it's still going to be sunny and it's down low on the horizon. Moves into its inferior conjunction on the 26th, after which it will be turned to the morning sky. Now, once it goes out through its inferior conjunction, it starts to run back behind the sun again. Now, it only takes 44 days to get to its superior conjunction at fair heights. So if you want to see it, it's a morning object after the 26th of February, and apparently it's not really going to be worth getting up for. Venus is a very bright object out in the western evening sky at the moment, as it approaches its longest or maximum elongation on the 25th of next month. So it's getting to the point where pretty good to view, and nearly 50-50 of the planet. So you'll see it as basically a half Venus. Earth reaches its autumn equinox on the 20th of March. Winter is coming, for those of you what's going to front. The equinox basically is the sun is over the equator, days just as long as night. So, and next one, Mars is still a morning object. The reason for that is we're actually chasing Mars around the sun, we're catching it. And I believe it's around about October when it reaches opposition, and in actual fact it's when Earth will catch it up and move in between Mars and the sun. And so sun's that way, Mars is the other way, in opposition, best time to view it. And they're hoping won't have the sandstorms that had last year, which obscured some of the detail. Jupiter in Sagittarius, it's a little bit behind Mars. It's also a morning object. It's just gone past its conjunction. Well, it didn't move into conjunction. We moved it into conjunction because the Earth travels a lot faster. And right behind that is Saturn. It's now moved past conjunction, and it's in the morning skies in Sagittarius, joined by Mars, Jupiter and Pluto. So you've got 4 planets in Sagittarius at the moment. 3 of them you'll be able to pick. The other one, better take a few shots over the course of a few nights. Pick a little dot that moves. Uranus, found in Aries, western evening sky. It's going to be in Aries until 2024, so you've got a few years to learn which one's Aries. So you can have a look at it, or get a go-to telescope. It'll be fairly low in the western sky as it moves into conjunction with the sun. So it's not going to be the best viewing object. And Neptune is slightly ahead of it. It's very low in the western sky, and it's approaching its conjunction next month with the Sun. So not a good time to be viewing Neptune either. Appearance of the planets. Basically, Mercury and Venus go through the same sort of phases as what the Moon does, depending on where they are in their orbit. Obviously, Mercury up the top here moves through fairly quickly. Now, in that position there, it's slightly to the other side of the Sun, so we're seeing most of its lit face. But as it moves around into maximum elongation, you will see that's like basically a half planet. And as it moves into inferior conjunction, it'll have its back turned to us. We'll see mostly black, and you'll see a crescent. Venus seems slightly more than 50% because it's still moving into maximum elongation, so it's kind of on the other side of the Sun at the moment, so it still has more of a lit face pointing to us. Mars, over the next few months, that will get slightly bigger as we move towards putting it into opposition. Saturn and Jupiter pretty well look like that all the time. You're just going to have to get up in the morning now to see them. And Uranus, Neptune, and Pluto in Sagittarius, galactic centre, take your pick. If you look at it, eyeball every little dot in that area and you can say you've seen Pluto.
So most of them was all visible on the 15th of February then, Mark, at different times? All on the same day?
You've got four in Sagittarius, so might be worth getting up in the morning for. Pluto moves past its conjunction with the Sun, returns to the morning sky, and as I said earlier, it's in Sagittarius with a planetary meeting being held by Mars, Jupiter and Saturn, but it's only a minor planet, so I don't expect it'll really get much of a vote. And minor planets in opposition this month. By minor planets, we're talking about asteroids, Kuiper belt objects and that sort of stuff. You can tell by the magnitude column here that they're not the brightest object. Anything greater than 6, or lower magnitude than 6, is pretty well not visible to the naked eye. Okay, I put this up all for the astrophotography guys who maybe like to take a shot at some of these, because you see 3 of them are in Cancer and 2 of them are in Sexton. So if you wanted to take a couple of pictures of that part of the sky and maybe pick out which one's which. Now, as the add-on tonight, I'm going to talk about an orrery. So most people will go, a what? Okay, an orrery is a mechanical device designed to represent aspects of the solar system, and when it's properly set up, you can use it to determine where things are in the sky relative to Earth. You can work out whether they're a morning object or an evening object. There are a variety of them. I actually threw one down over there, which is looks like a moon and sun and lunar orrery. Quite a few varieties of them. That's a rather flash one, but looks like it only does the visible planets. So there's the Earth there, usually with a little moon, and it's generally geared so that as the Earth goes around its gear, the moon will turn about 12 times. Well, not about 12 times, we should turn it 12 times. Mercury, it'll move fairly fast. You'll see these move, but Jupiter and Saturn will move a little bit slower.
You got one of them in your garage, Mark?
You what?
You got one of them in your garage?
I've got one of them in the box right there.
Okay.
Not that one. Okay. So that's an orrery.
It's interesting to note, by the way, with that is the planes of the orbits are actually slanting on it, so they bother to
yes, but I know
do
but
that.
it's a little bit hard to represent that on a mechanical device.
But that was actually on that previous slide. It was actually showing
too. I've got a lunar orbiter that's actually allows for the moon's 5 degree incline. But it's not the one I brought. This is the one I brought with me tonight.
Wow.
So it does work. Well, did the Sabo anyway, I made sure of it. It has a rather improbable astronomical alignment,
Where do you get that?
but that was purely for packaging purposes.
It's set up for your dot, is it, at the moment?
You got any furniture in your house, Mark?
The beginning of time.
No,
Where it's all rockets and models?
The orrery. Okay, so you can actually set it up. Comes with an Allen key. You can undo the planets. You can move them to where their various positions are. I'll find the switch.
Let there be lights.
Look at that. Work better if it's on. You can see Mercury. You might be able to see Mercury, but it's taken off. Venus is moving fairly rapidly, as is Earth and Mars. The rest of them are lagging behind. So I'll just leave that run. But when you look at the orrery there, you can see you've got Mercury, you've got Venus. These are the two minor planets, and Mercury goes around about 4 times in the time that Earth does. You can see the gear here, which allows Earth to rotate. It's not representing a day. It actually allows the little moon here to rotate every month. So it'll do one circuit every month. Now the way you set them up is you set them up with so that Earth takes 36.5 seconds to travel once around. So 1 second represents 10 days. Now the only downside is it hasn't got a counter, so you've actually got to keep tabs on what year you're looking at as it moves. So looking at that one there, if that's the sun, well that's representing the sun, so the face, we're kind of looking at the back of the Earth, so this is night time here. So at the moment, Saturn's pretty well in opposition. There's the sun, there's the Earth, there's Saturn out the back. This is Neptune. It's also to an extent in opposition. Mars is just, well Earth has obviously overtaken Mars, and Mars would be starting to get low on the horizon of an evening. Alright, this side here, that's morning. So all these objects out here are morning objects, if you can see them.
This is for the northern hemisphere.
It's got, if you count the number of planets there, there's a few extras. It actually has one representing the largest of the asteroids, Ceres. It also has Pluto and Eris. Eris is another Kuiper belt object. Okay, so I'll leave that running, and once that I finish, if you want to come up and have a look at it. You can see Jupiter's now moved a fair way away, and I appear to have lost Ceres. Hopefully it's in the box.
Where did you get it
Oh,
from?
no, it wasn't. It was Saturn.
Where did you get
I
it
lost
from?
Saturn. So, very important one.
You get it on eBay?
No, this,
Or you get it from a pawnbroker?
it came as in 100 weekly parts, and you had to assemble it. It's good fun assembling it until you realise it's got to be repetitious and that sort of stuff. But that includes a little motor in the bottom there, and all these gears up here are designed for each planet to rotate at a relative speed to each other. Now, as you can see, I don't know how many times I lost count, but Mercury's been whizzing around there at a fairly rapid rate, as has Venus. Even the Earth, been a couple of years since I turned it on. But in that time, Saturn has only moved from here, and Jupiter has only moved from here as well. So, take 12 years, go around the sun, that one takes nearly 30. Alrighty, so that's the orrery. And as usual, nice information was provided by Astronomy 2020 by Wallace Bores and Caulfield. Any questions?
Just something to add. Venus from now on to when it's in
Maximum
inferior
elongation.
conjunction is visible during the day. So in other words,
if you knew where to look, yeah.
yeah, but the way you work out to look and this is what I used to do when I was at high school, you get the age, which has the rising and setting times of the planets, and you simply divide the sky up, and that gives you an idea of what height it is above the eastern horizon in the morning. Or if you happen to have the moon quite close to where Venus is, you can go looking for the moon first. But it is easily visible with the naked eye. In fact, when it's in opposition, you can actually see with the naked eye a slight crescent.
In opposition? Your Venus is never in opposition.
I mean, opposition to Earth.
No, Venus is never opposite to Earth.
But, yeah, well, the Earth is in opposition to Venus then, put it the other way around. You can actually see it's a crescent. I have seen it once as a crescent. But it's very small.
All right. Any other questions?
No. Okay.
Thanks, Mark.
Thank you. I'll leave that running.
Yeah, come on.
See you, mate. See you, Peter. See you.
I've only seen it as a crescent once with the naked eye. And that was when I was a lot younger. I would suspect it was
Did you see it's in the circle?
Oh no, it's a normal rainbow. It looked like a normal rainbow, as we normally see during the day. Shades of bronze. I'm travelling on the freeway.
We think it would be very strange because of the woman in the back seat, physics girl.
Yeah, we're gonna go get right now.
It is, look, I'm not gonna keep you in suspense. Laser hair removal. We want to talk about the science that makes laser hair removal work.
I told him about this idea probably a year ago, and then I was gonna do it in July or August. And I've been waiting for this moment.
Yeah.
So
Now I'm scared.
now you're scared? Here we go.
Oh, yes. It stinks. Oh,
I went
man.
directly into your nose.
Yeah, it did.
It's called laser plume.
Laser
It's
plume?
actually
Is that
a word for
that's
it.
the smoke that comes off.
That's the smoke, yeah.
How was that shot? The laser we're using has a wavelength of 1064 nanometers, meaning it is infrared radiation invisible to the naked eye. But without an infrared filter, the camera sensor picks up the laser pulses, which in my case were 6 at a time, each one lasting about 1.5 milliseconds. We dialed it up a little.
We dialed it up just a tad.
Nice.
Ready?
The laser will now deliver 25 joules of energy per square centimeter.
Oh, wow.
That might be a really good
That was
Now we're talking.
Oh my god. Alright, so you're gonna want to watch this one.
Whoa. Oh my god. That is
There's
insane.
5 bursts. Did you see that?
Yeah. It looks like a shootout of the OK Corral. That's what that looks like.
It does. It totally
All the
does.
hairs are just getting slaughtered. That is amazing. That is an awesome shot.
That's sick. That's really sick.
I had no idea there was a shootout at the OK Corral. That makes me really kind of reignites my excitement about my job. So that's awesome.
I'm gonna get even closer on this next one.
That'll be cool. So what's actually going on here? Well, dark eyes, skin, and hair contain a molecule called melanin. And melanin absorbs a wide range of wavelengths of light, especially in the ultraviolet part of the spectrum. And this makes it an ideal shield against the sun's harmful rays, which is why you get a tan when you go out in the sun. That's your body producing and releasing more melanin in the skin. But the idea with laser hair removal is to get the melanin in dark hairs to absorb the laser light without the skin around it absorbing much of that energy. So it actually works best if you have really dark hairs and light skin. Infrared lasers are commonly used because melanin absorbs in this part of the spectrum more than other common molecules in the skin like water and oxyhemoglobin. Red lasers at 755 nanometers are also often used for the same reason. As the melanin absorbs the laser energy, the hair heats up to well over 100 degrees Celsius, causing it to burn and vaporizing the water it contains. And this puffs the hair up a little bit like a Cheeto. It's that expanding water vapor. Looking closely at this shot, you can actually see the bubbles on the hair from the vaporization of water. But the objective is not to destroy the hair. It's to actually use the hair to destroy the germ cells in the follicle that produce the hair in the first place. So it's kind of like using the hair to kill the hair. This image shows a cross-section of 3 hair follicles following a laser hair removal treatment. And the one in the middle contained little melanin and therefore shows no damage. The other 2 show the hair shaft has been destroyed, rupturing the inner root sheath and damaging the outer root sheath. Cells suffer damage when their temperature rises above 60 degrees Celsius. This is because at that temperature, the bonds in proteins and collagen molecules start breaking apart. And that's a process known as denaturation. So the hotter it is and the longer that temperature is maintained, the more denaturation occurs and the higher the likelihood that that cell will die. Now, if you cause enough damage to the cells in the follicle that make the hair will never grow back. And that is the goal of laser hair removal. This sequence of ultra-short pulses is used to ensure that the heat doesn't spread too far into the region surrounding the hair. So the idea is the hair heats up, damages the germ cells right next to it, but then the laser light turns off before that heat can spread too much further. And then you hit the hair with another very short pulse again. If you were instead just to keep heating the hair, it would heat not only the germ cells around it, but also your skin that you don't want to damage, and you would end up with burns. So that's the reason for the series of pulses that we saw. But if you think about it, this is kind of a weird irony. I mean, melanin is a molecule meant to protect us, meant to protect our skin from the harsh rays of sunlight, and that's why it absorbs that light before it can penetrate further into your body and do damage. But now with laser hair removal, we're using melanin, its unique absorption powers, against it. By overpowering it with lots of laser energy, we get it to heat up the hair to such high temperatures that the hair kills the neighboring cells, the germ cells in the follicle that produce the hair. And so we are using melanin's powers against it. Normally before a laser hair removal procedure, the hair is shaved, and that serves a few purposes. For one thing, not too much energy goes into burning the external hair, which does you no good in the first place. And second, it prevents the hot hair from landing on the skin and causing surface burns. But we found that shaved patches were less interesting to watch because you can't really see what's happening under the skin. After the creation of the first working laser in 1960, its inventor, Theodor Manin, called it a solution looking for a problem. And unwanted hair may just be that problem, because laser hair removal is the most requested cosmetic procedure.
That's number 1, hair removal.
Oh, that was gross.
How do they aim the laser so accurately?
On the head.
Hi, everyone. Welcome back to Cody's lab. So I have a sample of indium here. It has some tooth marks in it because this is the same sample of indium that I bit a couple of years ago in my biting indium video. Just like that. Now, in that video, I mentioned that indium was incredibly soft. And it is. Indium is one of the softest metals. And I also mentioned that indium was about the same hardness as sodium. Well, I've been working with sodium a lot lately, and I have to say that's not exactly accurate. Sodium is so soft that you can actually squeeze it and smash it in your fingers. Indium, on the other hand, you really can't do that with this. You know, I'm squeezing as hard as I can, and it's barely deforming. So I'd say indium is quite a bit harder than metallic sodium. Now, I know the first thing that you guys are going to comment on is, why don't you take a bite out of the sodium? Because it's softer than indium, you should be able to bite through it. And this is true. Biting into sodium, though, sounds like a very terrible idea because it reacts vigorously with water, and your body's mostly made out of water. But from working with sodium as much as I have, I think I might be able to get away with it, so long as I'm very quick and I mostly touch my teeth, because my teeth don't really contain much water. I am going to recommend you guys don't try this at home. Usually I don't say that because it's sort of hypocritical, because here I am doing it at home, but this is one thing that's rather dangerous. There's a small possibility of having a Coulomb explosion going on in my mouth, and that sounds like a very bad idea. But here we go. Let's try it out. So, I'm going to dry my teeth off here. Just take a bite out of this. There you go. A little bit tangy. I think the splatters onto my face from putting it into the water so close to me was a little bit worse than actually biting it, but there we have it. Some sodium with some teeth marks in it. That was unpleasant, but obviously I survived. A little bit tangy. I don't think it caused any damage, really. Really turned the very tip of my tongue into soap, but I'll recover. So there you go, biting sodium. In fact, Kenny, you want to kind of get a close-up shot of me doing that for the thumbnail? I think I'll actually bite it, but I won't bite all the way through. I'll just kind of put my teeth on it. Oh, that sodium bits on my nose here. Come on. Wait for you to get this out. Here we go. Okay, ready? So, here's a piece of sodium. It is covered in oil, so that's probably helping me. It's hot and very mineral oily. There you go. Now, I know a lot of you guys are probably going to want me to try tasting potassium. The sodium basically just tastes like regular old table salt, really, except a little more tangy. Potassium tastes like bananas. At least the potassium salts do. I haven't actually ever tried the potassium metal. Now, potassium is a bit more reactive than sodium. So much so that it will instantly ignite on contact with water. So I'm not really going to try biting through. I'm not even going to try biting this at all, actually. The risk of a Coulomb explosion is much higher. Let's cut a little piece of this off so you guys can see how hard this is. Potassium is much softer than even sodium is. In fact, it's about similar to what sodium is to indium. See, I can just pull it apart with my fingers here. It's a very soft metal. In fact, potassium is so soft you can actually squeeze it through a syringe if you push really hard. But, like I was saying, it instantly ignites on contact with water. So, here we go. Kenny's going to do a high speed of this. See? I'd rather it not do that in my mouth, so I'm not going to try biting potassium. So, there you go. Hope you all enjoyed, and see you next time.
Not the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody, this one's going to be bad!
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone.
That is more like very on point,
Science. But I believe we can go one better. There is one more alkali metal we can really use.
Yes, Richard, Caesium, the emperor of alkali metals, particularly nasty to go off at any time.
And that's it.
Oh, yes.
I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave it.
Thank you.
Okay, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion.
Makes me want to become a chemist.
And the last one is on parallel universes. Goes for about 10 minutes, but if you have to leave early, by all means get up and leave before we close the meeting.
But that begs another question, which is very interesting and very controversial. Could there also be other universes, and do we have any evidence for this? Before we talk about other universes, parallel universes, let's remind ourselves what we mean by our universe first. Our universe does not mean everything that exists. It simply means the part of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang. So this is our universe. If space is bigger than that, then there are other universes, other regions of the same size farther away. If you want to know what's happening in a galaxy over here, you have to wait billions of years more for light to reach us. We cannot see anything outside of our universe. One of the reasons this is so controversial is because many people say, oh, this is just stupid philosophical nonsense, you know. If we can never, by definition, see parallel universes, then it must mean it's not science. It's like talking about ghosts or something else that you can't see. But it's actually more interesting than this, because parallel universes are not a theory. They're a prediction from certain theories, which we can in turn test in various other ways. So to explain what I mean by this, let's look at another theory first. Einstein's theory of gravity, general relativity. It predicts a whole bunch of stuff which we can test and observe, like the motion of Mercury around the sun, the bending of light by stars, the time dilation that you can measure with your GPS and your phone, etc. And because of this, we take general relativity very seriously as a scientific theory, which means we have to take seriously everything it predicts, even things that it predicts that we cannot actually observe. Like what happens when you fall into a black hole. Einstein's theory of general relativity predicts exactly what happens inside black holes, but I cannot go observe it and then come and publish the results in a scientific journal here on Earth. It's impossible, right? But if one of my colleagues says, hey, Max, I don't like black holes, they can't just opt out of black holes. It's predicted by the theory. If they want to get rid of the black holes, they actually have to invent a different theory of gravity, another mathematical theory that's different from Einstein's, which doesn't have black holes, but which can explain everything else that Einstein did. And that has proven very hard, so hard that after 100 years or so of trying, many of the smartest people on the planet have failed to do that. The point here is that for a theory to be scientific, you don't have to be able to observe everything it predicts. You just have to be able to observe at least one thing that it predicts. And if that convinces you to believe in the theory, you have to also take seriously the other stuff it says. Now, what does this have to do with parallel universes? Well, first of all, we have a different theory, the theory of inflation in cosmology. It's also a scientific theory. It predicts a whole bunch of things we have tested and observed very carefully in the cosmic microwave background radiation and three-dimensional galaxy maps. It's right now the most popular theory in my field for what put the bang into our Big Bang. It was pioneered by Alan Guth and Andre Linde and others. It's a beautiful mathematical theory. And it also predicts parallel universes. In particular, it predicts that space itself isn't just really big, but that space is actually bigger than our universe, maybe even infinitely big. So the logic is that if inflation theory is correct, that we take it seriously, we have to take seriously the idea that space is bigger than our universe, that there are parallel universes, other regions of space that are just too far away from it for us to see. I call these parallel universes the level 1 parallel universes because they're not that different from our universe. The only difference is that over there, the particles started out in different places, so the galaxies formed in different ways, and if there are people over there, they will still learn the same things in physics class, but they might learn different things in history class, because things started out differently and history unfolded differently. The fascinating thing about parallel universes is that the most interesting question now really to me isn't whether there are any, but how many different kinds there are. And this is the least controversial kind, the first level. Then there's level 2. And that's something that you end up with if you combine theory of inflation with one more idea. If it turns out that string theory, or loop quantum gravity, or whatever the ultimate correct theory is going to be, that unifies all of physics, if it turns out that that theory has more than one solution, with a homogeneous space in it, kind of like the equations for water, and have 3 different solutions. Liquid water, ice, and steam. Then this theory of inflation actually will create not just a big space, but it'll create a big space with each of these solutions actually happening. So the theory of inflation actually converts potentiality into reality. It'll make a universe with this kind of space, with that kind of space, with a third kind of space. Some string theorists think that there's 10 to the power 500 different kinds of space even. And what does it feel like to live in one of those parallel universes if they exist? Well, more interesting and diverse than in the level 1 kind, because they wouldn't only learn different things in history class, they would actually learn different things in physics class. They might learn, for example, that there are not 6 kinds of quarks, which is what I learned in physics class, but that there are 10 kinds of quarks, or 2 kinds of quarks. Many of the properties that we thought were fundamental properties of physics, according to string theory, are just telling you which particular solution of string theory you're in. Do these exist? We don't know, of course. How can we test it? Well, by testing inflation more and by studying string theory more to see if it seems to make any sense or not. If it does make sense, though, it actually would help answer another big mystery we have in physics, which is when you look around us in the world, our universe has all these numbers built into it we call constants of physics. For example, there's a number that tells us how much dark energy there is. The value of the number is about 10 to the power minus 123. 0.000 blah, 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 1 with 123 zeros. And if you imagine that you could make your own universe, and you can have a little dial, a little knob that can change each of these numbers, I would recommend don't touch those knobs, because it turns out almost anything you change by a little bit will kill all life. If you put in more dark energy than we have by a lot, you destroy all the galaxies. Dark energy prevents them from forming, for example. If you change another number to do with the Higgs particle, suddenly you can't have any atoms. And this is a deep mystery in physics. Why is it that our universe has these numbers which seem to be fine-tuned for life? Is this just luck? Is it some kind of miracle, or what? Well, the level 2 parallel parallel universes actually give a scientific explanation for this. Steven Weinberg made a famous argument many years ago when he said that suppose the level 2 multiverse exists and the amount of dark energy is different in different parts of space. Then you predict something like the Sahara Desert. You know, most of it is dead, no life, no galaxies. But there will be still, you know, some places where where the dark energy has exactly the right value to allow galaxies. And that's, of course, where we should expect to find ourselves. If I know that I'm a Bedouin and I live in the Sahara Desert, I'm not going to be surprised to know that I live in an oasis. That's the only place that there are people really living in. And it paints this picture where the same thing is happening on a larger scale in our cosmos. After this prediction was made, dark energy was discovered. And a Nobel Prize was given for it. And this has made people take this idea quite a bit more seriously. It's still fair to say that it's very controversial. We don't know, but it's certainly a scientific question we can discuss, whether our reality is this big. We should also be mindful that we humans have again and again made this mistake of underestimating the size of our cosmos. First we thought Earth was the center of everything, right? Then we discovered that our solar system existed in a galaxy and the universe. So it might very well happen again. There's no guarantee in the laws of physics that we humans should be able to see everything that exists. And if we cannot, by definition, there are parallel universes. Well, and there's even more. There's a third kind of parallel universes which have come into the scientific discussion from studying not the biggest things, but from studying the smallest things, by studying quantum mechanics, the rules that govern how atoms and elementary particles behave. This is arguably the most successful theory in all of science. It's given us transistors, computers, cell phones, lasers, etc. But at the cost of some weird ideas. Quantum mechanics tells us that little particles can be in several places at once. If the particles can be in several places at once, well, I'm made of these particles. I should be able to be in several places at once as well. And in 1957, a young graduate student named Hugh Everett worked this out really carefully and argued that what it really means is that there is a third kind of parallel universes, where when you make certain decisions, effectively our world splits into several parallel tracks. If I get a parking ticket, there's a parallel universe maybe where I didn't. But there's another parallel universe maybe where my car was stolen instead. So you win some, you lose some. This sounds very philosophical, but it's the way to test this, again, is not by speculating, but by studying quantum mechanics more. In particular, we should try to build quantum computers, which is a kind of machine which takes advantage of parallel computation and effectively using these parallel worlds. If we try to build them, and there are millions and millions of dollars spent right now to try to do so, if it fails, because we notice that the basic equation of quantum mechanics is wrong, then we can forget about all these parallel universes. But if they succeed, and they can calculate something in 5 minutes that would take longer than the age of our universe to do on a normal computer, I think that will make many scientists take these parallel universes more seriously.
Yeah. Okay, and with that, I'll close February's meeting, and hopefully we'll see you here at March's meeting.
There's another question I wanted to ask that guy before too. Yes.
So if quantum computing really succeeds, then internet security starts.
Exactly.
You can crack AES 256.
That's a good one.
Like that.
Exactly. I would imagine they would be.
Maybe it can be harmed.
Flat plane.
Maybe it can be harmed. They would use some.
They're going in the wrong direction. We see them flat plane.
Sometimes when you keep talking, sky for the mushroom. I saw sometimes satellite giving the northern hemisphere direction. I think.
This is why you give them a call. I'm going to
See, the orreries, but I think
it's
that
just
was
like
the
we're
best
standing
one.
on the